Welcome to the video lecture. This week we're going to be discussing neural engineering and the neural engineering framework. So there are three parts to the neural engineering framework. First is population coding, the next is transformations, and then dynamics. So let's get into population coding. So the goal here is to learn how to systematically encode, decode, and transform data stored in the activity of a population of neurons. So if we know what processing we want done by a neural network, how do we design a network to do it effectively? Can we build a compiler to implement a program on a neural machine? So like for any machine, we will add a hardware abstraction layer between our data processing and the hardware. When you're writing a program in Python, you have an idea of what you want to happen to the data. You don't worry about how it's being implemented on the processor. So that's the idea of a hardware abstraction layer. You think about the data processing, not about the hardware implementation. So this approach will allow us to focus on the data that we are encoding and the transformations applied to that data. So far, the way we've thought about neural networks is kind of a black box. I know that we know everything that's going on inside the network, but in terms of it learning, it's really just an input, which might be X, goes into this black box, and then out goes our output Y. And we don't really control what happens inside the neural network. Neural engineering is a bit different. You have your input, X, and it's going to go into some box, but it's not going to be a black box. It's going to be a box for which the function that's evaluated is controlled by us. It's going to have some output Y, and then we could even have another one that output goes into another population G, when we prescribe what function we want that population to perform as well. Finally, we get output, I'll call it Z, equals G of f of X. So by putting these two populations together, we can essentially evaluate this chain of functions. So we can build a neural network that processes our data by putting together a bunch of regression layers. So each of those populations is trained as a regression layer. So for population coding, the first step is to encode data into the collective activity of a population of neurons. So consider this simple regression network with an imaginary linear readout node. That's this over here. So we're just going to imagine that the readout node is there. It doesn't actually have to be there, but this is part of the philosophy of encoding and decoding, or at least understanding how a population of neurons can collectively encode something. So this imaginary linear readout node is going to be connected to all the neurons in the hidden layer. So on this slide over here, we call this encoding. And it's going to be a bunch of weights and biases. And then it goes in the hidden layer, H1, H2, H3, down to H, capital N. Now when we have this imaginary decoding unit, Y, you can look at the weights D1, D2, D3, all the way down to D, capital N. So these weights are called decoding weights. And we have Y equals H1 D1 plus H2 D2 plus dot 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 plus H, whoops, that's a D, HN DN. You could also write that as a dot product, of course. You could say it's all those H's, H1 to HN, dotted with D1 to DN, or if you like, H dot D. I guess you could also say, if these are, I think in this lecture we'll be using column vectors. I'll have to think about that. Oh, okay. So H is a row vector, and D we need to be a column. So I'll write it like that, D transpose. I guess I mean H times D transpose. On the left, it's the dot product. On the right there, this thing here is more of a matrix operation. Okay. So now suppose we want our imaginary readout node to approximate X. So the input was X, the hidden layer is encoding X, and we want to see if we can decode that value from that hidden layer. Now we have to have a specific range that we're going to decode that for. You'll see why later. So we want to be able to decode X for a range of possible input X values. This is essentially a regression problem, but we will only consider changing the decoding weights, and we're going to leave the encoding weights alone. So it's a regression problem, but we're only going to control these decoding weights. The encoding is basically going to be random. We just accept whatever it is. But since we're going from a low dimensional data to a high dimensional hidden layer, there are lots of random encodings that still maintain that information. It's not like an autoencoder where we're going from a high dimensional input to a lower dimensional latent space. In that case, you have to be really careful, and you have to kind of come up, or the network has to come up with a compression strategy to maintain the information, that sort of the statistically salient information in the input data set. In this case, it's kind of the opposite. We're going from low dimensional, projecting it into this high dimensional representation, and trusting that the information's still there, and you'll see it is. Okay, where was I? Since we know what function we want, did I read the other part? We'll only consider changing the decoding weights. Done that, yes. Since we know what function we want our network to compute, we can create our own training data set. So I already said we want to decode out X. So we basically want our little neural network to represent the identity function, if you like. So first thing we're going to do is choose a bunch of X values. We're going to make our data set. Choose a bunch of X values in whatever range that we're interested in. And here I've got all these X values. There are capital P of them. And we're going to generate samples from those. So the inputs are these XPs, and the targets are the same things. This is like an autoencoder. In fact, this network up here is an autoencoder in the way we're currently treating it now. The difference is the latent or the hidden layer is much bigger than the input and output, as opposed to an autoencoder where the input and output are high dimensional and the latent layer is smaller. So it's a different philosophy. We're not trying to do that the sort of representational learning that you would do in a typical autoencoder. This is just a bit like an autoencoder because the input and the output happen to be the same. But you'll see pretty soon the input and output don't have to be the same. We can learn other transformations. Okay, now how do we learn the decoding weights? So the output of our network, remember, is our hidden representation, which depends on our input, dotted with D. Or if I just sort of get rid of the dependency on X, and now I'm just using the dot product here. So what we want to do is minimize over the different possible D decoding weights the expected value of our loss between our output and our target, which is the X value. Which is minimizing over D the expected value of our loss between H dotted with D. That's a dot. Still a dot. Okay. Now, since this is a regression problem, we're going to use the mean squared error. It's typical to use that for regression. Okay, however, let's look more closely at this optimization problem. So we're looking to minimize over different D's the 1/2. Mean squared error has that 1/2 factor, which is not very interesting. don't worry about it. But of course, we're dividing by p also, because it's the mean squared error. We have to divide by the number of samples in our data set, times the sum over all of our points, p equals 1 to capital P, of this thing, h dotted with d minus x. Okay, so that's the MSE loss. Now we can write that in a slightly different form. Instead of having the sum, I mean, the mean squared error adds up over all the elements in a vector anyway. So if you have a vector like this, and you take the L2 norm of it, that L2 norm basically, L2 norm squared, it actually adds up down the column anyway. So so this summation we can actually just represent as a bunch of vector elements. So let me show you. 1 over 2p, we're minimizing over decoding weights d, this thing. So putting all capital P elements into the same formula, into a vector, just piling them up vertically, it's like V stack, vertical stacking. We have h1 dotted with d, h2, so this is the second sample, dotted with d. Now these h's are the activities in the hidden node, in the hidden layer, right? So we're multiplying all these, the hidden layer activities, by the decoding weights. And those hidden layer activities are from each of the different inputs, each of the capital P different inputs that we're processing and learning on in our training set. So that thing there should spit out a vector with P elements in it, a column of P elements. And we know what we want them to be. We want them, the first one to be x1, we want the second one to be x2, and so on, down to x. That should be capital P, sorry, not n. Two squared, okay. Which we can really just write as 1 over 2p minimizing over decoding weights, capital H times d, let me write it like this now, d transpose minus x. So that d is a column vector. That's by default in this course, the vectors are row vectors, so that vector needs to be a column vector. I guess that's just above me right now. Okay, now that capital H thing is this. It's basically taking all these different hidden layer activations for over all the different samples and putting them as rows in this H matrix. So it's H1 in the first row, H2 in the second row. So each of these is all the neurons. Each row is recording all the neurons for a given sample, down to HP. Hewlett-Packard. Okay, so that H holds the activities of the hidden population with each row corresponding to one input sample. Okay, so that capital H basically, it's like, think of it like a batch, the activity of the hidden layer for a whole batch. So optimal linear decoding is this. Given a set of P inputs stored in capital X, so that capital X is a column vector. Each row, if you like, is a one vector of an input sample. And we pile them up, sample, 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 sample. Given a set of P inputs stored in X, the corresponding and the corresponding activations, this H matrix, these are, for example, could be firing rates, neural activities, whatever they are. The optimal linear decoding weights, D star, solve argmin D H times D transpose minus X L2 norm squared. And those weights can be computed by solving the normal equations. So D star, I guess, I'm going to get myself into trouble here because the notes I'm reading from do not transpose the D vector. But I've decided while I'm giving this lecture that the D has to be a row vector, so bear with me. So this formula for computing the least squares solution, the normal equations, are for when D is a column vector. So since my D is a row vector, I'm taking the transpose to make it into a column vector. I hope that makes sense. Okay, what's the solution of the normal equations? H transpose H inverse H transpose times X. The normal equations. Okay. So that works. Let me see if I can demonstrate that. Here I've got a bunch of Python code that demonstrates these sorts of ideas. So here I've basically got a single layer. It's basically linear, and then output is, the activation function in the hidden layer is just logistic. And I've got my encoding weights, and I'm going to worry about the decoding weights later. This is my decoding weights. So the forward running into the hidden layer and back out is just encode the value X and then decode that hidden activity. So 10 neurons, and let's look at what these neurons look like. So this is what we call the tuning functions and tuning curves. So for different input values from -1 to 1, this is all 10 of my hidden nodes, their activity over those various different inputs. You can see these curves look different. Why? Because each neuron in the hidden layer has a different input weight, different connection weight, and a different bias. So these are all logistic functions, but they're shifted and they're potentially flipped and scaled, like shrunken and expanded horizontally. Okay, so those are the tuning curves. So let's try encoding some number. It's going to be a random number. I don't know what it is. Isn't that exciting? So put it into my network, and then what am I doing? Right, this shows the activity of all 10 of my hidden nodes for that random input. So it's 10 neurons. You can see vertically it's showing the activity of each of them. Now, if I were to look at those activities and try to match them up with this plot here, where along this plot do all those activities match up vertically? And you can see I've done the work here. It's right over here. You can see that all those activities match up. So the idea is that given those activities, we can infer what the input was. It looks like it's about 7.748 or something. So let's see what it was. 0.739. Something like that. Okay. So the idea is that from the hidden layer alone, you can infer what value was encoded. In this case, we encoded 0.74, and from matching up these dots to the tuning curves, we can see it's about 0.74. Now that's all great, but can we do better than just eyeballing them? Yes, we can. We can find these decoding weights so that when we multiply those hidden layer activities by the decoding weights, it'll spit out a number close to 0.74. Okay. So we haven't trained the network yet. We haven't trained the decoding weights yet. So let's look at what it looks like when we just run a whole bunch of inputs through into our hidden layer and then decode them with random decoding weights. So, oh, there's my cat. Excuse me. His name's Babu. He likes to walk on keyboards. Okay. Where were we? Right, so the input was numbers between -1 and 1, and if it's going to decode that value x, then what we want output is the same value. So when we input -0.5, we want output -0.5. But when we multiply by the decoding weights, we don't get that behavior. You see for an input of -0.5, the output's 0.3 or something, 0.35. It's not what we want. That's fine, we haven't trained it yet. So we could train these weights using backprop, which is what we've been doing so far. We have random encoders, but we can train the decoders using backprop. So here I'm in Atom, you can tell it what parameters you want to use. I'm only giving it the parameters of the decoder, the decoding population, that linear layer. Mean squared error loss. I'm going to run 5,000 epochs, so giving it a whole bunch of points. And so I run a whole bunch of my test x points through it. And lo and behold, I do get the output looks a lot like the input. So I've trained only the decoding weights now using backprop to decode the value that was encoded. So now we can actually think of the collective activity of a population of neurons as encoding a particular value, and we know how to decode that value. So we've sort of taken the mystery out of what this hidden layer is doing. We know how to encode values into it, and we know how to decode values from it. So that was using PyTorch and backprop. But I just showed you how you could use least squares. The reason we can use least squares is because there's only the decoding weights. There's no nonlinearity that we're worried about. The nonlinearity happens before we get to the hidden activities. Once we have the hidden activities, the nonlinearity has already been processed. Decoding from there is a linear operation. So that's why least squares works. We don't have to do backprop by this gradient descent optimization. We have a formula for it just using linear algebra, least squares. So I'm going to hide from you the way we solve this because that's part of your assignment. But it's wrapped up in a function somewhere. So d star is now that set of decoding weights that is a solution of the least squares problem. And now if I use those weights, I can take so h is I take my x's, my x values, and I encode them. Then I do this thing to turn it into NumPy. So that I get h. This is a collection of all my hidden layer activities. And I multiply all those hidden layer activities by my decoding weights, and I should get an approximation of what the input was, x bar. And I do. The output is very close to what the input was. And this way I did my decoding by just a matrix vector multiplication, but equivalently I could have basically taken my d star weights and set the weights of my PyTorch linear layer. And this does exactly the same thing. It does the same, because that linear layer is just really doing a matrix multiplication. Okay, let me go back now to the notes. So now we know how to encode, well, if we encode information into a population of neurons, we know how to train the optimal linear decoders to decode the value that was encoded. Turns out there's nothing really special about what we encoded. We can encode nonlinear functions of what was encoded. We can also encode, I'll get to that in a minute, we can also encode vectors. So here we have two inputs to this neural network. I've got x1 and x2 and a hidden population again. It could be the same number of hidden nodes as before, but now instead of just encoding, having the collective activities of the hidden layer representing one number, I want the collective activity of those hidden neurons to represent or encode two numbers. You could think of it as, I was going to say like a latent space, except this is a higher dimensional thing. Okay, so what we have then is, let's look at going from x1, the first input, to all these hidden nodes. Okay, so that kind of does what we were already looking at. So if we look at one sample, our h is going to be some nonlinear function. What do we run through the nonlinear function? Now, you don't have to write this down because I'm going to fix this in a minute. x1, whatever that is, times some encoding vector. So in this case, the e would be the weights. I don't know why I'm doing it that direction. Yes, I do. No, I don't. Do I? Yes. Yeah, that makes sense. This is for row vectors. Good. Okay. And so that E is basically the connection weight matrix going from x1 to this hidden layer. And I've drawn it red. Now, if we actually have two things we want to input, then our input vector could actually be x1, x2. So those are two separate elements. And now we'll want to have a second set of encoding weights, which I'm drawing as blue here. So that E, the set of decoding weights now, goes from 2 dimensions to n dimensions. So it's a 2 by n matrix. And then we'd have to have a bias as well. So this bias is an n. So let me put some numbers on here. Well, variables. Okay, now when we have p samples, like that, our h is going to be sigma of x times our encoding weights plus, as you saw before, a whole bunch of 1s times b yes. So this x here is going to have one sample per row. Now each sample is a 2 vector, right? So it's going to be like that. It's going to be p tall and 2 wide. So this way we can process our whole input data set or batch of inputs, whatever, and encode them into a single activation matrix that records all of our hidden nodes for all of our samples. Okay. Now we just have to find 2 sets of decoding weights because we're encoding 2 different values. If we want to be able to decode those, we're going to have 2 sets of decoding weights. Shown here is the gray decoding weights and the light blue decoding weights. And we'd want y1 to be equal to x1 and y2 to be equal to x2. So we have to find 2 sets of decoding weights. So D star transpose, I believe, is argmin over D of, turns out it's the same formula. Except we're using the Frobenius norm. Frobenius norm. And this D now, or this D transpose, let me think about this for just a second. Is that supposed to be transposed there? I guess we want that to be transposed. So this whole thing here has 2 columns. One for each output node. So that means this thing here has two columns. Yes, because ultimately we're decoding two vectors. So each row has to decode to a two vector. Okay. Okay, here's a joke. I was driving and my friend said to me, "Have you ever fallen asleep while driving?" And I said, "No. I've woken up while driving though." Okay, finally we can decode nonlinear functions of the encoded value. So not only can we encode and decode vectors of values, but we can even do nonlinear functions of those things that were encoded. We can encode, when we encode x, we can decode not just x, but we can decode nonlinear functions of x, like sine of x, or absolute value of x. Or if we encode x and y, we can decode x times y, nonlinear functions of the things that were encoded. So, as the example with which I just gave, suppose a population of neurons is encoding x1, x2. We can decode t of x1, x2, some nonlinear function. In this case, I'm saying it's the product of x1 and x2. So we're encoding two values. We're decoding just one value, but it's going to be the product of it's going to be this nonlinear function of the two inputs. It's really just the same mathematics. All we have to do is solve a different least squares problem. So let's let t equal this vector. The first element is the first sample x1 times x2, just multiplying those two values together. The next output that we want is the same thing, the x1 times x2, but for sample 2. That's a mess. Let me fix that. x1 from sample 1 times x2 from sample... Let me do it again. x1 from sample 2 times x2 from sample 2. I did it! And so on, all the way down to the pth one. x1 from the pth sample times x2 from the pth sample. So this is not two columns. This is not a matrix with two columns. This is a vector with a single column. Each column happens to be the formula of the product of x1 and x2. So then, it's the same formula as before. Argmin over d of h times d transpose minus t Frobenius norm squared. So the only difference is that we have a t there instead of x. So instead of saying we want to decode the value that we encoded, it doesn't matter what we put there. We could put anything there and say, please decode that for us. As long as it's consistent and not asking for similar inputs to output drastically different values, then we should be able to find a decent least squared set of decoding weights for that. And in general, as long as an error can be supplied, as long as you can, whenever you evaluate your hidden layer and you decode them, as long as you can get a measure of that error, maybe that error is actually coming from a different part of the brain, you can train the decoding weights. Okay, you don't even need to be able to formulate that this t outputs that you want. As long as you have from somewhere you have this error that you can send into to this least squares problem, you can adjust those decoding weights to try to make that error minimized. Okay, so let me show you that working for nonlinear functions. So decoding nonlinear functions. Here I've got the same code, except this time instead of, like, I've got my x as input and I've evaluated it through through my first layer into the hidden layer, through my first layer of weights into my hidden layer. So H is the activities in the hidden layer. Now what I want to decode, I'm just going to take the absolute value of x. Instead of decoding x, I'm going to decode the absolute value of x. And then I put those into my least squares problem. And this is what I get out. So it's not perfect. I'm having a little bit of difficulty here. But if I use more neurons, this is with only, I think, did I say 10 neurons or something? Or if I used more neurons, it'd have far more sort of fitting resources to draw from to fit that better. So let me show you Nengo. It's a different, so Nengo is like a software platform that was created here at the University of Waterloo by another professor who's in systems design engineering and philosophy. His name's Chris Elias-Smith. So he's really developed all of this neural engineering framework quite a lot. So this program called Nengo is from his lab. So what we have here is just a population of neurons. It looks like it's 5 neurons, but that's just the visualization. It's actually 20 neurons, and they called it an ensemble. It's a population or ensemble of 20 neurons. Now, if I look at these neurons, I can look at the tuning curves. So it's randomly computed some encoding weights and biases. And so given those weights and biases, you can see what the tuning curves for each of the 20 hidden neurons is. Now it automatically computes the decoding weights. And so now this stimulus here is something I can control. So let me go like this. Now I can look at the spikes coming out of that population. Go like this. So when I say go, it's really fast. It's showing me 10 of the 20 neurons. Now you can see, let me slow it down a little bit. You can see there's this spike raster has a certain pattern. Now when I change the input, the pattern changes. Now it changes because each of the neurons in this hidden layer has a different tuning curve, so it reacts differently to the stimulus. Now I can ask for the value. I can ask it to give me the value. So this is the value it's decoding from this hidden layer encoding. So it's already computed the decoding weights, and it's decoding the value from the hidden representation. You can see that it matches what I input. My computer's having trouble, I think, because I'm doing video capture, screen capture, and running this all at the same time. I guess that's why. Who knows why. Anyway, so this is actually using leaky integrate and fire neurons, spiking leaky integrate and fire neurons, and it's decoding from them. That's why it looks kind of noisy there. I can change, well, I won't play with it too much. Anyway, you can see that you can use Nengo to pretty easily create this this population coding scenario. I could encode also 2 values. Let's see, node 0, 0. I have to make the dimensions of this population 2 now. So now it's encoding 2 things, and it's got 2 different sets of decoding weights now, and I can, if I change the input that it's being, for this 2 vector that's being encoded, I can change the inputs, and it knows how to sort of disambiguate those. It knows how to infer each of those 2 values from the collective activity. So see as, let me just stop this for a second. Let me show all of them. So this is all 20 neurons. You can see as I change the x1, the values, the spiking pattern changes. And as I change x2, the spiking pattern changes. So these neurons are actually changing, reacting to 2 different inputs. So if you look at only one neuron, that's not enough information to figure out these two values. But with 20 neurons or more, that's enough information to figure out what these two different inputs were. Okay. So let's go back to the notes. We're nearing the end here of this population coding lecture. So word about solving the normal equations. Now, the normal equations look like this. If we're decoding the x from x could be t or whatever, that's not the point. The point though is that if this thing here is almost not invertible, then that can be a problem. It can become a nearly singular problem that's hard to invert. Moreover, if it's close to singular, so it doesn't have to be exactly singular, if it's ill-conditioned, that can be a problem. If it is close to ill-conditioned, then your solution is going to be very, very sensitive to noise that's in H from the neurons or noise that's in X from your encoded values. So to sort of guard against that, we can actually add a regularization to this least squares solution idea. So let's suppose that there is H error. There's error in our hidden neuron activities. So I'm going to represent that as epsilon. So H plus epsilon. Epsilon is basically a noise matrix that's the same size as H, but we're going to assume that every one of those neurons has normal, identically ID, independent and identically distributed random variables. Okay, so I can rewrite that as HD. I'm just going to write the D as, well, I guess I should do D transpose. That shouldn't be a problem. Yeah. Minus T plus epsilon D transpose, Frobenius norm squared. Let's just say the two norm. Let's just say we're talking about vectors here, and all the same stuff applies whether we're doing Frobenius norm or not. Frobenius norm, you can actually just take your multiple. If you're decoding more than one number, you can actually just separate those two problems into two completely separate least squares problems. Okay, so without loss of generality, we only have to look at one column, solving one column in D transpose. Okay, so I can rewrite this thing over here as HD transpose minus T plus epsilon D transpose, all that transpose, times the same thing but not transposed. So multiplying that out, I get terms like this. HD transpose minus T transpose times HD transpose minus T. So that's multiplying this one times this one. Now multiplying this times this and this times this actually gives the same thing twice. One of them is just the transpose of the other. But they're actually, since these are just scalars like this, the value of this thing is just a scalar. So the transpose of a scalar is the same as the number not transposed. So I can combine those two terms together. So it becomes plus 2 times HD transpose minus T times epsilon D transpose. That should be transposed. Yep. Okay. Plus D times epsilon transpose epsilon times D transpose. Okay. Now, since this noise here is independent of that error, that should basically on average give us 0. Hope you can accept that. This last term here, epsilon transpose times epsilon. Now this is just basically a vector of Gaussian noise times a vector of Gaussian noise. In general, that gives you a 0 again, because these are independently drawn samples, so their correlation should be 0. Except when it's one of the one column of epsilon times the same column, those are perfectly correlated. So that epsilon transpose times epsilon is basically a scaled version of the identity matrix, and the scale that we multiply the identity matrix by is sigma squared, where sigma is basically the standard deviation of epsilon. So those epsilons are taken from a normal distribution, mean 0, and variance sigma squared. So this last term is really just d squared, if you like, or let me write it out. So this first term just becomes h times d transpose minus t squared, so the original least squares problem. And then we have plus sigma squared times so if d is a matrix, or sorry, a vector, then we just use the vector 2 norm. So what that last term there, so this is the original least squares problem. And this thing here looks like regularization. Basically, it's like an L2 regularization. Now, let me just say it is L2 regularization. So it's basically weight decay. This basically is a regularization method that stops you from being able to fit too much noise. And you can put a weight on that term, and the weight that you can choose is what you think the variance of the error in your hidden node activities are. But really, you can just put anything there, and it'll help regularize your solution. So thus, the point of all this is that it can be helpful and stabilizing to add a bit of noise to your hidden layer activities before you put them into least squares. So instead of solving this problem down here, you are effectively solving it by just adding noise to your hidden layer activities first before you ask for the least squares solution. Adding noise basically it regularizes it because it kind of removes any coincidental, or it removes the ability for the least squares problem to match the minutia in your data set, because since there's more noise, it's just going to have to kind of go through the middle of your point cloud instead of being able to sort of wobble up and down and fit all the weirdness in your data set. So thus, it can be helpful to add a bit of noise to your activation matrix before solving the least squared problem. I'll stop right there. So I hope you learned something about population coding. The encoders are random, but we can solve for the decoding weights using a linear least squares problem. And that way we can basically specify what computation we want that layer to do individually.